Okay, so today we're going to do Chapter 10, the two sections that are left for the entire course. Yay, right? And we're doing correlation. So correlation is one variable has a relationship with another variable. So a correlation, the two variables are somehow related. So for example, many times in classes, the very first out of the gate test, I will run a correlation based upon students' homework scores and their test score to find out if there is a correlation. One would think that the homework being completed would give a higher test score. You would expect a correlation to be there, right? Sometimes there's an outlier, so I'm going to be using a lot of those terms, outlier. And the outlier could be that somebody got a very high score on the test, but they didn't do their homework. Is that possible? Absolutely. Because sometimes they may have taken the class before. Maybe they're one of those people who can just sit in class and get it without doing any practice. I could never do that. I had to practice all the math that I learned. So, but I've seen people that can do that. So is it perfect? No, it doesn't have to be perfect. But that's what we're going to be talking about. Okay? And in that, we're going to be running a test for that linear regression. We're only doing linear regressions. And we're going to be using something called the linear coefficient, R, which measures the strength of the relationship. And we're going to be using that R value to decide if the linear regression, which is actually a line, is a good predictor. That's really it in a complete nutshell. So let's talk about what you might be seeing here. Some room. So let's say I decided to plot homework scores and compare them to test scores. We might have something like this. This is called a scatter plot. We might have an outlier where they didn't have to do their homework, but they got the high score. But what a linear correlation does when we run that, it takes all of this data into consideration and it creates a line. And as long as it's a linear relationship. And that line might be going through the data that looks like about there. Is it perfect? Does every point lie on that line? No. R is equal to the measure of the strength. Then we're going to be able to use that table that just got distributed, if everybody got one, A6, to, are there any more? Did anybody have an extra one? Might have to share. To see if it is a good linear relationship to make a prediction. Okay? Now, sometimes you'll find out that you need to, bless you, you need to run the test, you need to find the linear relationship without an outlier, because that outlier can change your line dramatically. And basically what I drew here was without the consideration of that outlier. If I were to guesstimate, and that's all I'm doing with these lines, by the way, if I had included that, think about what I would have to do. This line would have to curve a little bit, come up, wouldn't it? I would be changing the y-intercept, and it would be changing the slope of the line. And it may be something more like that. So that one outlier would have a dramatic effect on my linear regression. Linear regression is going to be y is equal to mx plus b. And you all remember that from algebra, right? Good. Excellent. Okay, so you can see some graphs up there. When I look at these, and you'll have to look at your stats plot, and we'll show you how to do all that, to see if this is approximately a linear relationship. When I look at this one here, yeah, that looks pretty darn good. It looks like they're all kind of gathered around the line. Same thing here, even though this would be positive, right? Because, bless you, I'm going uphill from left to right. This one would show a negative slope, wouldn't it? Going downhill left to right. And that's okay. It can be positive and it can be negative. There's my R values for those two plots. This one, however, is just random dots all over the place. There's no linear relationship there. And I might get an R close to 0 there. Okay? This is, if you run this, you're going to get an R, but it's wrong. That's why it's important to look at your stat plot. This is not a line. This, to me, looks exactly like, anybody know? What does that look a shape of? A normal distribution. I didn't even think of that because I'm thinking of functions. I'm in my algebra mode right now. I'm thinking of a quadratic, a parabola. Yep, that's what I'm seeing when I look at those scatter plots. That's not linear. And even though this is a pretty high, well, it will be a low. This one's a low one. It's not going to be because it's not linear. Okay? So we have those things that are going on even when we're looking for a linear relationship. So here's the requirements. It has to be paired data. It has to be a simple random sample. A visual examination of the scatter plot. That's what I just showed you, a scatter plot. It has to look like there is a linear relationship. Okay? It's got to approximate a line. I have to watch out for those outliers. I have to be aware of those outliers, and any must be removed if they are known to be errors or the effects of the outliers should be recalculated or without the outliers included. So if I suspect an outlier and I get rid of that outlier in my data, then I rerun it and R is strong, that indicates that's going to be an outlier. Okay? So here you go, rounding. Anytime we do the calculation for R, we're going to round it to 3 decimal places. And you have that table A6 in front of you, so that kind of reminds you because they're all 3 decimal places there. Here's some common errors. The one that I said, homework scores and test scores, probably are a cause. But because of that, sometimes we assume that correlation implies causality. It doesn't have to. You could just be comparing 2 things, and there is a strong relationship, but one does not cause the other. So that's a common misconception. For instance, here was one that for several years we had data that suggested a linear relationship, that the number of the stork population and the number of human births. When we look at that, guess what? there's a linear relationship, and it's a strong relationship. Do the number of storks have any calls? Do they cause higher number of births? Absolutely not. Okay? Absolutely not. So we can have a lurking variable. Who remembers what a lurking variable is? We're all sleeping. We're all ready for turkey. A lurking variable is something that we didn't make sure. Yeah, we want to exclude that from the possibility. So one of the examples is, I always think about this one because we're always in education, obviously. So 2 classes are going to be blind tested with 2 different textbooks and software that supports them. Okay? A lurking variable is that you have, by just random, one group is already stronger than the other group when they first came into the class. That's a lurking variable. We didn't get rid of that. We could have matched everybody in the classes based upon their GPA, say. I'm just pulling something out. It could be that if I'm going to teach both, I really like this textbook and this software better than I like the other one. Which one am I going to do a better job at? The one I like. That's a lurking variable. Okay? That's what we mean by a lurking variable. We should not use data which are averages. We should not use data which are averages, because the averages don't look at the variation of the individual data, and our correlation coefficient usually comes out much higher. So we don't want to look at averages because it suppresses individual data. Okay? And the third error involves the property of linearity. There's really no linear correlation. There might be some correlation, but there's not a linear correlation. So that's the 3 errors we usually see. So here's one. Lemons and car crashes. Listed below are annual data for various years. The data are weights in metric tons of lemons imported from Mexico to the United States and car crash fatality rates per 100,000 of the population. Is there sufficient evidence to conclude that a linear correlation between weights of lemons and imports to the U.S. car fatality rates? Do the data results suggest that imported lemons cause car fatalities first? What you got to say? How can the import of lemons have any effect on the number of car crashes with fatalities? Okay, seriously? So we can even answer that without doing anything, right? But let's get those calculators out. So we're going to let our x variable be the lemon imports and the crash fatality rate be our y variable. Just like we did before, we're going to go into second and stat because that's our list. Sorry, don't go that way. Go to stat, not second stat. We're going to go in and we're going to edit our data in our list. So of course I'm going to go into my list. If you have data in there, you remember how to clear it out. cursor up, press clear, and then press enter. And let's go ahead and enter the data. Again, the lemon imports in Y1. I always do that. I hit the backspace and it says, nope, you can't backspace here. In L2, of course, we're going to put the fatality rate of car crashes per 100,000. Once you've got that data in, we need to look at our scatter plots to see if there's a linear relationship going on. So the way you're going to do that is you're going to second and stat plot, which is above the y equals sign. And this is what you should see, the menu like that comes up. We're going to click on enter because we want to look at plot 1. See where it's blinking right now, it's solid on off. We're going to hit enter on to turn that on. Coming down, the type is already highlighted there. That is a scatter plot, so that's what I want, is a scatter plot. For your X list, you're going to put L1, if it's not already there. For your Y list, you're going to put L2, and your mark is going to be that little square. If it's not there, remember how to get L1 and L2 is simply by clicking second number 1 and second number 2 for L1, L2. Is everybody okay? So then I'm going to have you hit zoom. Oh, I got to get out of that first, sorry. Hit zoom, cursor all the way down until you get to zoom stat.
How did you get to Zoom?
Um, I got out of that. I just said second quit. And then I hit the zoom button. And then cursor down to zoom stat. Does everybody get it? You should see a screen like mine. Okay? What that zoom stat is doing is it's changing the values of your window to match the values that you need for the data that you put in. That's all zoom stat does. So you can actually see here, this is my actual data points that have been plotted. So what's your gut say? Is it kind of looking like the shape of a line? Yeah. Yeah, and it actually looks like the shape of a line. It's pretty darn good, actually. And is it going to have a positive slope or a negative slope? It is going to have a negative slope. And that's okay. We can still have a strong linear relationship. Okay? So, that's all that 10.2 really talks about. Somebody, are you surprised? But let's go back to our notes. And, well, before you do that, go ahead and everybody go ahead. Did we answer the question? Is there sufficient evidence to conclude that there is a linear correlation between the weights of lemons? Well, we think there is. Let's go ahead and run the test. So here's how we're going to run the test. First, go to y equals. We're plots on. We're good. I just wanted to check that. So we're going to go to stat. We're going to cursor over to tests. Okay. I'm waiting so you can write it down and follow me at the same time. You're going to cursor all the way down till it says, on mine it's F. It may not be F on yours if you have a different operating system. Linear regression, and it says t-test. Linear regression, t-test. Everybody cool? Go ahead and press enter. And here's where you have to make sure that you have your things set. X list should be L1. Your Y list should be L2. Your frequency should be 1. And the one that's highlighted is not equal to. Is everybody cool there? Okay, you're going to cursor down to where it says reg equation. That means regression equation. Here's how you're going to put this in there so it automatically copies what it gives you and puts it into your Y so that you can see it. So you're going to go to vars, cursor over to Y vars, choose number 1 for function, and then once you get to your function screen, choose number 1 for Y1. And what it did is it told the calculator, once you find the regression equation, regression line function, you're going to take that and paste it into our graph for Y1. That's what it's saying. So I'm going to cursor down and hit calculate and hit enter. And this is going to give us a lot more information that than what we need, but notice at the top of the screen there it says y is equal to ax plus or a plus bx. That's a little differently than you're used to seeing y is equal to mx plus b. It's a little bit different. All they did was switch the order. So a is actually your y-intercept and B is your slope. A is your y-intercept and B is your slope of your line, okay? Because it's doing a t-test, it's giving me the t-value, it's giving me a p-value. We all know what p-value means, right? So our p-value is 0.009. So it's going to be really close, really good. It's going to fall way out there to the end, right? Because we know our areas. It's even giving us our degrees of freedom, which is 3. And for this calculation, notice it's 1, 2, 3, 4, 5 pieces of data. In this case, it's the number of data minus 2. But it gives us the degrees of freedom. Here's my A, 16.49. That's my y-intercept. I'm going to cursor down, and I've got B here. B is my slope of my line, and it's negative 0.0028. Okay? I'm going to continue to cursor down, but I want to write this real quick. But you know, when I go to write, it's going to get rid of my calculator. So I'm going to do y is equal to negative 0.00282 x plus, what was my intercept?
26.
And what it's going to do in your calculator, it's going to switch these to 16.49 minus 0.00282x. It's the same thing as y is equal to mx plus b. All they did was switch that order. Just know that A is what? Your y-intercept, and B is your slope. So back to your calculator screen there. What we're looking for and what we actually have to get to here is this final line which says R. R is the correlation coefficient. The correlation coefficient. Remember, the correlation coefficient gives us an actual measure of the strength of that relationship. And it says R is equal to negative 0.9589. Okay? So, then you have to go to your table A6. Table A6. It didn't give you what you're testing at the level, but we're going to go 0.05. You notice your N is your first column. 0.05 alpha is the middle column, and the last column is a 0.01. Okay, so we're going to look at 0.05. I had N, the number of pieces of data I put in were 5. My correlation coefficient says 0.878. 0.878. So what that means is I have lots of problems there. I shouldn't even be drawing a curve. Let's just draw a number line. My correlation has to be between -1 and 1. Has to be. 0 is no relationship. -1 is a perfect negative slope. +1 is a perfect positive slope. When we looked at table A6, it was 0.878 for an alpha of 0.05. So that means 0.878 negative 0.878. Okay? In between here, no relationship. Here and here. What one did I come up with on my calculator? Our R was negative 0.9. We're going to round to 3 places, negative 959, negative 59, I didn't say it right, negative 959. Where is that going to fall on my number line? Yes, between these two, right? So I'm going to say, oh, let's get green. Somewhere about here is this, correct? So it is a good relationship. Absolutely is a good relationship. My linear equation is going to be a good predictor. That's what that means. My linear regression equation will be a good predictor. So the next year, if I had, let's see, how many tons? If the next year I have imported 425, is that in tons of metric tons of lemons, I could make a prediction based on that how many fatalities there would be per 100,000 crashes. That's what that means. Okay? If it falls where there's no relationship, I cannot use that linear regression equation. It's not good. It's not a good predictor. Instead, I'm just going to take the average. Instead, I'm just going to take the average, the mean. Okay, so I know I went ahead and just like, I always do that, blurt out the whole lesson, but let's keep going. We'll come back to those. Oh, there's my strategies for predicting Y. See, I told you that ahead of time. Is the regression equation a good model? In our case, was yes. So because of that, I am going to use my regression equation to make a prediction. If it had not been, I'm going to just use the mean. I'm just going to use the mean. That's all I'm going to use. Okay? So we've talked about slope. We've talked about our regression equation. We found the regression equation. Now we're just going to talk about something called marginal change. It's how much one thing changes to the next. Our marginal change is really nothing more than we know it to be a slope. It's the same thing we think of in algebra as slope. How much does it change each time? What's the average mean change between the data? Okay. We also talked about an outlier. We saw what an outlier would look like, and it's a point just way out of line with the other data points. You can have one or more influential points, which are points that strongly move that graph of that regression line, and I showed you one of those with just a sketch. Okay, here's another really good sketch. So original paired shoe print and height data. Why would we even look at that? You think that's true? You think that one has any cause? We don't even have to have cause. Or is there any relationship? Look at people. Yes, why? Very good. You're absolutely right. George said that tall people, basically, you didn't come out and say this, but I'll come out and say it. Tall people have bigger feet, right? Shorter people have smaller feet. If not, we wouldn't be able to balance to stand up, right? It's the physics of our body. So we think there might be a relationship then between the paired shoe print and height. So now we're not just looking at feet, we're looking at the actual shoe print. Okay? So here's our data for one set of data. And look what happens if we use one additional point. One additional point. Wow. Look at the line. Look at the slope. How dramatically different is that? This is such an influential point, we would use the other line. But why do you think that might happen, that this person has a very long shoe print but is very short? Why could that be? Is that possible? Maybe. Maybe. Maybe we measured wrong. It could be an error. Maybe they were wearing their clown shoes. Maybe they're trying to disguise it. And, you know, you've seen shoes that have those long pointed toes, okay? Yes, absolutely. I agree with that. So yes, it could be a real error. Not a real error, but a real person they measured correctly. But you can see where that one needs to be excluded, right? Totally changes. Totally changes. Okay, so another definition, residual plot. Residual plot. The residual is the difference between the actual data point and the predicted data point. The difference between the actual data point and the predicted data point. So let's go back and look at a graph so I can explain that a little bit better. Here we go. So this red line is my predicted values. My predicted values, because we took all those data points and we put them in there and we kind of went up. This is like where it's going to go through. And we get that y-intercept and we get that slope or that marginal change. But we know that every data point doesn't lie on that line, does it? We know that's true. So the difference, the residual, is the difference between the actual data point and the predicted data point. The actual data point and the predicted data point. And we're going to measure all of those and add them up. Would be the sum of the residual plots. But that's what it means by residuals. The difference between the predicted and the actual. Okay? Well, we're going to plot those in our calculator. We can see it, and I'll show you how to do that. But this first one is what we want to see, and that's going to indicate to us that the equation is a good model. That linear regression equation is a good model. It means here's my even point here, and all of these are the differences. These are all the residuals. It's scattered all over the place. There's no pattern whatsoever. That indicates it's a good relationship. This one kind of has a pattern, doesn't it? It kind of looks like it does this. Almost looks like a sine wave to me. There's a pattern. Not a good, the equation is not a good model. Not a good model. Then this situation starts here, but then it branches out and gets wider. Not a good model. Not a good equation. I want to see this one, where it's all over the place. This is the one I want to see. That means it is a good model for that equation. Okay? And this is the one that I found that I thought was really good. So you actually have this. I do it slightly different because I just use a different way of putting in my my plot 2. I put it in plot 2. So we're going to go back to our calculator. Let me just get to my home screen. Second quick, go back to your home screen. And here it says we're going to add the residuals to list 3. This is exactly how I do it. So you don't even have to write this one down. So I use method 1, where I go to the main screen and I hit second and list. Scroll down to where it says residual, which is number 7. Press enter and say store. And the place we're going to store them is in L3. So we're going to go second L3. We're going to go ahead and hit enter. Now it's giving us the whole list of the residuals. They're all right there, but let's take a look at stat and edit to see our lists. And now you're going to see L1, L2, and L3. L3 is the residuals. Okay? So let's go to second quit. So I want to see my residual plot, though. I want to see what this looks like as compared to what one of those are. So I want to go to y equals. I want to cursor over on that equal sign for y1, and I want to press enter because it's going to turn that plot off. I don't want to see the line. I don't want to see our regression equation line. So I turned it off. I'm going to go to second plot. I like to have them both up there, so what I do for one is I just go in and turn one off. So I can go back and forth when I need to. Going now back up and over to plot 2. Cursoring over and going to plot 2. I'm going to come down and press on. So I'm turning on plot 2. I want a scatter plot, so I'm going to leave it just as it is. But here's the difference. Instead of saying X list L1 and Y list L2, I'm going to cursor down to Y list and change that to list 3 because that's where I put my residuals. So second L3. Okay. Everybody there? So I'm going to get out of there. Then I'm going to hit zoom. And again, I'm going to cursor right down to zoom stat. Press enter. And now I can see my residuals. They're kind of scattered all over the place. There's no pattern. So that was a good equation, regression equation model. I absolutely am. We're going to do a whole problem together from start to finish. Okay? There's a lot of steps in that, isn't there? I agree. Okay. So let's go. Of course, here we have it. Oh, but I'm not making you do data. Let's see if I've got one on here with data. Here we go. So number 23. We're going to do from very start to the finish. Find the best predicted systolic blood pressure in the left arm given the systolic blood pressure in the right arm is 100 milligrams. So I have data here that is my right arm. I have my left arm data. Oh, do you need one of these? Okay. I think it's the last page of your notes. Isn't it? Is it the last page of your notes? Yes? Okay. And then I copied extra, the same problems over again. I'm not realizing they were on here. Okay, so here's the key, though, you have to look at. You got to read it carefully. Find the best predicted systolic blood pressure in the left arm. What am I predicting? I'm predicting the left arm, given the right arm. Okay? So because I'm predicting the left arm has to be my L2 or Y. So that's key. I'm predicting the left arm, so the left arm has to be going in L2, which is going to be my Y. That means my right arm has to go in L1, and that really is my X. Okay, so let's go in and enter the data first. I'm going to edit my lists. Now that we have our data entered, the first thing we want to do is just look at a stat plot of the data to see if it has any linear relationship. Okay? So to do that, we're going to go to our second stat plot. This is why I put the residuals always in plot 2, because that means I don't have to change anything. I just turn them on and turn them off. So for plot 1, I'm going to go into that and click on so that that plot 1 is on. Okay. I'm going to cursor up and cursor over to plot 2. Hit enter, and right now I want plot 2 off, because that's why I use my plot 2 for my residuals. So I use plot 1 for my stat plot and plot 2 for my residuals. That way I don't have to keep changing whether it's L1, L2, or L3. Once I get that set, it just stays like that. Your screen looks different. Let me take a look. Are you pressing enter to go into the stat? Okay, so now press enter. Okay, so there you are. So right now you've got stat plot 1 is on. So cursor up and then cursor over to stat plot 2. Hit enter. And it's already off, so you're set to roll. Okay? Okay, so you are, so 2 is off. Go up over there and hit that, and it says 1's on. Okay? Everybody okay? Okay. The other way that I can tell which ones are on and off is by looking across the top where it says plot 1, plot 2, plot 3. Whatever one is, well, no, it's not. It's on the other screen, sorry. So I'm going to do second quit, and then I can show you. Everybody second quit and get out of that stat plot. You're going to go to zoom and cursor down to zoom stat. Remember, that's going to adjust my window to fit the data that I've put in. Or if not, if you don't do that, your data might not even be shown on your screen. Because, you know, the last time we had, what, 15.7, 15.9, blah, blah, blah. Those were some of our data. But this time our data is 79, 82, 104. So it has to adjust the window so we can see it. That's what Zoom Stat is doing. Zoom Stat. Yeah, it should be Zoom Stat. Let me take a look. Okay. Yes. So here's the data that I have. It kind of maybe it's a linear, but I don't know that it has a lot of strength to it. But at least it's not a pattern. It's not all over the place. So we're going to continue our tests. So here's there. So now I'm going to just go second quit and get out of that. I'm going to hit my stat. I'm going to cursor over to tests. I'm going to cursor all the way down to where it says linear regression t-test. Once I'm on linear regression t-test, I'm going to hit enter. Once you have that in, it should stay in your calculator. That's why you always use L1, L2, and L3 the way we're saying, then you don't have to change these things. So my X list is L1, my Y list is L2, my frequency is 1, everything is there, and now since I've already put in my regression equation to Y1, it's still there. I don't have to redo that. How do you do that? Let me cursor down and I'll go through those steps again. So I'm going to delete it. And this is how I'm going to get it there. I'm going to click on vars. I'm going to cursor over to yvars. I'm going to choose number 1 for function. And I'm going to choose number 1, y1. And hit enter. And now it will be there. Okay? Cursor down, I'm going to hit calculator and hit enter. And now it's going to give me all these numbers back. Again, where's my t? There's my p-value. Degrees of freedom, these are things I don't really need. What I need to know is that A. Again, A is what? Yeah, and it is my y-intercept. My B is my slope or marginal change. Okay? And we're going to cursor all the way down, and we're going to find that our R value is 0.867. My R value is 0.867. How many pieces of data did I have to put in there? 5. So I'm going to go to my table A6. Looking at table A6, we'll do an alpha of 0.05. And for 5 pieces of data, what is the requirement there? Point 0.8 what? 0.878? 0.878 positive, negative 0.878. The R that I got was 0.867. 867. Where's 867 going to fall? Is it going to fall out here to the end or close to this one on between the 0 and that? So it's going to be right about there somewhere, right? So that's going to be 0.867. When it falls here, no relationship. It's too weak. It's too weak. So it's no relationship. Oh, the problem will tell you which alpha. It just says sometimes it's up there, all those instructions. I don't copy them all over. So, and I shouldn't say no relationship. I should say not a good predictor for the linear regression. So it's not a good predictor. Okay? So since it's not a good predictor, if I wanted the prediction, I would not use my linear relationship. Instead, what I'm trying to predict is the left arm. I'd simply find the mean. That would be the best prediction I could make, is to simply find the mean, because this failed my test. It failed my test. Okay? Right, because that's what I want the prediction of, the left arm. So I'm just going to take the left arm data and find the mean, because my linear regression is not a good predictor. Okay? Now, you could do it that way, absolutely. Yep. Okay? Sound good? I could simply just add them all up and divide by 5, right? That's my mean. Okay. So, do I really need to look at my residual plots? Not really, because I already found using R that it's not a good predictor. I could have at the very beginning looked also at my residual plots to see it's probably not going to be one. Okay? Just for practice, let's go through the residual plots and how to do them. That's the handout I gave you. I'm going to start back at my home screen. And the first thing I need to do is get those residuals into L3. And the way I'm going to do that is second list. Then I'm going to cursor down to residuals. I'm going to press enter. Then I'm going to tell the calculator to store those values into my L3 list. So I'm going to hit the button Store. Then second, number 3, because that's L3. Press enter. And all of those differences between the actual data point and the predictor are now stored into L3. Okay? Now I want to take a look at the residual plots. Now this is where I have to go play with my stat plot. So I'm going to go second and stat plot. And this is why I always put the residuals in plot 2, because now since I have them set, all I have to do is turn them on and turn them off, turn them on and turn them off. Okay? So I'm going to hit enter to go into plot 1. I'm going to cursor over and turn off plot 1 because I don't want to see the scatter plot. Instead, I want to see the residual plot. So then I'm going to cursor up and over to plot 2 and hit enter. Plot 2 is currently off. I'm going to press enter on, so I've turned plot 2 on. Everybody okay? I'm going to go to zoom. What am I going to go down to? Zoom stat. It's going to fix my window. So I have now my residual plots. So it was another way that I could look at it to find out, is the linear regression model a good model? And I see it's not, because why? It starts real thin here and it goes wide and goes wide. Let me see. Let me just hit pause on this recorder. Actually, we're done. And then I can do that and we can do some more problems for practice.